Welcome, everybody. In this video, I want to talk in detail about compound linear inequalities. So when we have two or more inequalities joined by the words either and or, we call these compound inequalities. So basically, you're trying to solve more than one inequality at the same time. So they're not two different problems. It's occurring within the same problem. And we usually either join them by the idea of and or. So let me start with and inequalities first. And before we begin, we're just going to talk briefly about what it means to be an intersection of two sets. So when two things intersect, it's where they overlap. So here's just a very quick Venn diagram. So here, let's say this is set A and this is set B. Well, where those two sets overlap, that would be their intersection. The notation we use for intersection is sort of like an upside down U. It reminds me of an N, so that's why I think of intersection when I see it. So here, just a very basic example. For instance, let's say set A were the values 2, 4, 6, and 8, and set B was 1, 2, 3, and 4. If I'm trying to look for where the sets intersect, I'm looking for where they overlap. So notice how they both have the value 2 in common and also the value 4 in common, right? Those are both in each of the sets. So that would be the intersection here. So the intersection of sets A and B would be the values 2 and 4. Now I am using set notation. Those are those little squiggly bars here, and just again listing the values out in this case because they're all listed. So the intersection is where they overlap or what they have in common. You can think of it that way too. So now let's look at some examples with inequalities. So when solving and compound inequalities, when we get a solution, it has to work for both inequalities. So that's the idea, is it can't just work in one of them, it has to work for both inequalities. So you really are looking at an intersection of the two solution sets here. Now, there are two different style of and problems. So the first style, you may have seen if you've watched my other videos, but this is what I like to call like the sandwich style. That's not a professional term here. I just think it looks like a sandwich, right? You have kind of two ends here and then the middle piece. So this is one type of and inequality. And basically what you're solving is you're solving this inequality and this inequality. So you have the left side and you have the right side. Now, this is a very particular case where both of those inequalities happen to have 4 minus x in common already as part of their expression. So it doesn't happen for every case, but if you had that repeat expression in two different inequalities, we often combine them together into one when we're solving and. So in this case here, the way we solve these style is we're still going to get x by itself, but we're going to work inner to outer here. So for instance, I need to get rid of this 4. And I would normally subtract it. So what I'm going to do is subtract it to all sides at once. So it's sort of a lazy or a shortcut way to solve more than one inequality in one shot, though. And then here I'd have to get rid of that -1. So I'm going to divide by -1. And again, because I'm really doing two problems in one, I do have to do it on both sides. So I do both inequalities at the same time. And don't forget with inequalities, if you do divide by a negative, you do have to change the direction of the inequality sign. So my answer now looks like this. So 2 is greater than x is greater than -3. We can also graph our solution sets here. So let's see, 0, -1, -2. Here's -3, 1, and 2. And what ends up happening in these particular and examples is you're shading in the middle. So they're showing you that x is in between 2 and -3. And then because there are no equal signs, I am going to use a parenthesis on either end there. Now you can also write this as interval notation. Remember that interval notation, we write left to right. So our leftmost shaded value is -3, and our rightmost shaded value is 2. And then we're going to mimic the symbols we see here. So it looks like this. It does sort of look like a point, but when you write it, this is called, again, interval notation. you're actually giving a range of values. So we're telling the reader that, hey, the solution set is all values in between -3 and 2. Let's do one more here. In this one, we have -2 is less than or equal to 2/3 x plus 5 is less than or equal to 2. So we have another one of those sandwich inequalities. I do see a fraction, so I like to always clear my fractions first. So I'm going to start by multiplying everything by 3, all sides. And don't forget that 3 in the middle is going to get distributed throughout. So on the left, you have 3 times -1. And then you have 3 times 2/3 x plus 3 times 5. And on the right, you have 3 times 2. So we end up with -3. Our 3's will cancel there, is less than or equal to 2x plus 15 is less than or equal to 6. And now I'm going to continue solving inside to outside. So I'm going to subtract that 15. And again, make sure you subtract it to all parts. So I have a 2x in the middle. Let's see, over here, I have a -9. And on this side, I have a -18, it looks like. I'm going to divide by 2. I'm dividing by a positive here, so I don't need to flip any inequality signs. And I have -9/2. And on the left here, I have -9. Okay. So let's go ahead and draw that graph as well. Now, if you need to, you may want to put -9/2 into your calculator. You do get -4.5, or you could change it to a mixed number and you get -4.5. It just helps for graphing, so you have a better idea of what you're graphing. So we're going down to -9 here. 8, 7, 6, 5, 4. So this is -5, -4, -3, -2, -1, 0, 1, 2. So I'm just putting a few key points here. And again, x is sandwiched in between -9 and -4.5. So about right there. Now, each of these does have the option for equality. So I would use a bracket on either end. So don't forget, when you have symbols like this or this, you're using bracket notation. If you have symbols like this or this, you're using parenthesis notation. So I'm going to use brackets there. And then I can also write it in interval notation. So I'm going from -9 is the smallest value to -9/2. And again, I would just mimic what is there with the brackets. The only time we don't kind of use the symbols as much is if you are going one way to infinity altogether, then infinities do always get parentheses when you're doing interval notation. So that is the exception. But otherwise, you're just using the symbol that is in the inequality problem. Okay. Now let's look at a couple examples of and problems where they are not sandwiches. So you can see here that I could not write this as a sandwich problem because I have totally different expressions, right? There's no way to kind of combine those in one. So in that case, you're going to solve each separately first. So here I'm going to add 7 to both sides. Let's see. We get x is less than 9. Here I'll subtract 1 from both sides. And then divide by 2. And I have x is less than 4. So I have here that x is less than 9 and also that x is less than 4. Now, if you're pretty good at just kind of reading problems and thinking about this through, you can probably figure out the answer here. But I usually like to graph to help myself. So what I'm going to do is I'm going to graph these both on the same number line. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we'll go up to 12. And I'm going to use 2 different colors. So I'm going to do this one in pink. So x is less than 9. We'll go like this. And there's no equal sign there, so there is a parenthesis. And then x is less than 4 would be right here. And again, I would use a parenthesis also. Now, this is something that's really great to do with highlighters, because highlighters color really easily. And when you go over them with each other, they change color pretty dramatically. If I had a pink and a yellow highlighter, it would switch to orange pretty clearly. So it's really nice if you do this with highlighters. And now what I'm looking for here, because it's an and problem, I want the overlap region. Right? So notice where are they overlapping? They're overlapping right in here. So that is my solution set for an and problem. It has to be the overlap or the intersection of the two. So they overlap from all values less than 4. Because I have a parenthesis on the 4 for this one, it's not included as the end value. So I'm going to use a parenthesis here as well because it's not, the value of 4 is not in both groups. Here it is strictly less than 4. So we're going to make sure that we don't include the 4 in our answer. So the final answer here is actually just that x is less than 4. That is where the overlap occurs. And if I were to draw my final graph, it would just be this. Right, so the first one is sort of a working graph. And for my interval notation here, it does keep going forever to the left, so that would be negative infinity, and it goes up to 4. Now I mimic the notation there, and infinities do always get parentheses for interval notation. All right, let's do one more and problem. So again, I'm just going to solve these separately. If you look at the expressions, there's really no way that you could combine these. So I have to just take my time and solve. On the left, I divided by 2. On the right, I'm starting by adding 1 to both sides, and then I'm going to divide by 4. So I have that x is greater than or equal to 0, and x is less than or equal to negative 2. So again, I like to draw them all on the same grid. I find that to be easiest. All right, so I'm going to do this one in pink. That would be x is greater than or equal to 0. So we're going in this direction. And there is a equality line there, so I'm going to use a bracket. And then for the other one, I need x is less than or equal to negative 2. So we're going this way. Now, don't forget, this is an and problem. So because it's an and problem, I need the overlap or the intersection. And hopefully what you're noticing here that there is no overlap, there is no intersection, right? So there are no solutions that actually work in both groups. That's what the intersection is. It's a set of values that work for both inequalities. So here, there are none of them. They don't overlap with their solutions at all. So in this particular case, there's actually no solution here. Depending on the text or how they want you to answer it, we could say no solution. Sometimes they'll write it like this with an empty set. So there's no number, there are no numbers in the set that work. Or they'll use a symbol like this. It looks like a 0 with a line through it, but it actually represents what we call the null set or the empty set. So meaning that there are no answers that work here. So those are a couple different ways that you can write this. As weird as it looks, if you were selecting a graph, you would actually select the graph with nothing on it. So if there's no intersection and you have to like graph it still, you would actually select a graph that has no shading because there are no answers there. It could also happen the other way. So if it works out where, you know, everything overlaps, you actually could have all real numbers for solutions. So like an identity there, although it's much rarer. But if everything overlaps, then that could be the case too. Again, although that's a little bit rarer here. But in this case, there's no overlapping section. So our answer is no solution. All right, the last I want to talk to you about in this video are or inequalities. So or is the opposite idea of and, right? So either or this can happen. So we use the idea of a union instead. So a union of two sets is when we unite two sets together or we just combine them. We bring them both together. So here's a quick Venn diagram. So if this is set A and this is set B, I'm not just looking for the intersection. I'm trying to combine them both totally together. And the symbol we use for unit is a U. Now, when you're entering homework, though, you do want to be careful. They will give you symbols like this. If you just type a regular U in, it may not recognize it as the union symbol. So I do suggest that you use the symbols given on homework assignments and things like that when you're typing. So here we have two sets. So let's say A is a set of x values such that x is an even integer that is greater than 0 and less than 10. Now, you don't have to, but it may help you to actually write out what these numbers are if you can, or at least see the pattern. So I need even numbers strictly greater than 0. So we're not starting at 0. So the first even number after that would be 2, right? 2, 4, 6. And it has to be strictly less than 10. So I'm only going up to 8 here because I have to be less than 10. So that's actually set A, is the numbers 2, 4, 6, and 8. Set B are the numbers 3, 4, 5, and 6. So I'm going to combine these together. That's what the union means. So I have 2, I have a 3, I have a 4, I have a 5, I have a 6, and I have an 8. Now notice that 2, 4, 6, and 8 are all included, and 3, 4, 5, and 6 are all included. When we write sets, you don't have to write them in order, but most people typically do. But they actually don't have to be in order. But we do not typically write repeats. So even though, the number 6 appears twice and the number 4, I don't write it twice. I just need to write it one time. All right, so let's look at a couple of solving equations now with inequalities for OR. All right, so when solving OR inequalities, a solution needs to work in at least one of the inequalities. It doesn't have to work in both of them. It just has to work in at least one of them. So this is an example of a union. We're going to combine our two solution sets together in the end. So we're not looking for the intersection. We're just looking to put them both together. There are no sandwich styles here. There's actually not a way that we can correctly write a sandwich-like problem for an OR one. So even if you have similar expressions, you have to write them separately. So I solve each of these individually. All right, so for the first one, I'm going to start by adding 3 to both sides. That gives me 5x is less than or equal to 13. And then I divide by 5, and I have x is less than or equal to 13/5. If you want to, 13/5 would be, let's see, 5 goes into 13 2 times, which is 10, and I have 3 left over. So 2 3/5. Here I would subtract 1 from both sides, and I have x is at least 4. And again, this is an OR problem. So I'm going to start by graphing them both on the same graph. Okay, so let's do this one in pink. So I'm looking at less than or equal to 2 3/5. So maybe like, right here, I'm going less than, and this is an equal sign, so I'm going to use a bracket there. And then for the other one, I'm going for a greater than or equal to 4. So I'm going in this direction. Now, because this is an OR problem, right? This is an OR problem. I don't care that these don't intersect. My final solution is both of these put together. So I'm just going to rewrite it just to kind of drive that point home. But your final solution set is just this. So it's both the graphs combined together. So for unions, we're taking both sections. And you can write your answer actually as x is less than or equal to 13/5, or x is greater than or equal to 4. So if you're writing it in set notation, there's really no way to combine those because they're two different sets. Like I can't simplify that at all. For interval notation, these do get a little bit weird. So you do have to write each piece separately. On the left side, it goes to -infinity and then up to 13/5. On the right side, it goes from 4 and it keeps going, so to positive infinity. And then what you do is you put a U in the middle for a union. So that's how you can write your interval notation if you have disjoint pieces on the graph. All right, last example. Again, we're just going to solve these separately. So I'm going to start here by adding 5 to both sides. I have -2x is less than 2. I divide both sides by -2. Don't forget you're dividing by a negative, so we are going to flip that inequality sign. So this becomes greater than -1. And then on the right here, we're going to divide by 6, and I have x is less than 0. And this is an OR problem. So let's see, -2, -1, 0, 1, 2. So we'll do this one in pink. X is greater than -1, so we're going in this direction. We'll do this one in yellow. x is less than 0, so I'm going in this direction. Now here, again, I don't want the overlap because everyone's like, oh, I can see where they overlap, right? I don't care about that here because this is an OR problem. So for an OR problem, I want everything that's shaded. And if I look carefully here, the whole line is shaded, right? There's no gaps or missing pieces like there was here. So your final graph then is actually going to be the whole thing shaded, right? Everything ends up being shaded in this case. So how can we write this as our answer? So you could say something like all real numbers. Or if we're doing interval notation here, we're going all the way from negative infinity to positive infinity, right? Everything is included. So this is how we can write all real numbers in interval notation. So the graph that you would be selecting is the one that's totally colored in. And again, the interval notation there would be negative infinity to infinity. So it's just really important that you read carefully if you have an and or if you have an or problem, because you can get obviously very different results. But otherwise, they work pretty similarly. It's just that final piece that you have to be careful. Are you looking for an intersection? Is it an and problem? Or are you looking for anything shaded, right? Putting it all together, which is a or problem.